Good evening. For this programme, we're going to concentrate on what we call the Kuiper Belt, strange, icy objects out and near the path of Pluto. But first of all, a few news notes nearer home, and beginning with Mars. Mars Express still going around the planet, and now we've discovered a whole mass of underground ice, a frozen sea.
That's right, it's this area here, Elysium Planetaria. It's a flat area, but if you look closely with Mars Express, you see what appear to be ice flows on the surface. Now, the area is quite near the equator, so how do they survive? Well, the suggestion is that they're covered in volcanic dust that protects them from the sun, and so we actually have icy areas, tens of miles across, appearing near the surface.
And that may be the area where we look for any kind of Martian life. I don't mean little green men, but any trace of Martian life at all.
No, the best guess is from counting craters on the surface,
Exactly.
is that these flows were formed 5 million years ago. Recent in geological terms, but it's
indeed.
not the same as saying there's water there today.
No.
For that, we need to look under the surface. We can either do that by going there and digging, or we should get some indications from the radar instrument on Mars Express, which is finally due to start working in the next couple of months.
Now, further out, of course, Saturn. We've seen those amazing results from Saturn's moon Titan, but results also from the planet and the other satellites, one called Enceladus, for example.
That's right. Cassini's just performed its first flyby of Enceladus, and we get another one in just a week or so. Now, this is the brightest, most reflective object anywhere in the solar system, so you'd think it was covered in ice, and that's what the results show. What was less expected, though, is its wrinkled surface.
So let's leave our solar system now and look further afield. One of the most amazing discoveries of recent times is that of a galaxy with no stars.
That's right. We'd always known from computer simulations that there should be more galaxies in the universe than we see. Small ones, perhaps, but they should be there. And finally, we found one. It's dark, it contains hydrogen, but it doesn't contain any stars.
Will stars develop there, do you think?
It's difficult to tell. All we know is that it's very faint. Astronomers have looked for the light that should be there. Nothing seen so far. We can't even tell you whether it has any normal matter at all in it. But one other point too. It's embarrassing that we don't know what most of the universe is made of, but we didn't even know where most of the normal matter, like made up of atoms like you and I, we didn't even know where that was. And Chandra, the NASA X-ray satellite, has been able to identify it. Faint, glowing gas, warm gas, in between clusters of galaxies. And it might be that almost half the normal matter in the universe is out there in the voids between the galaxies we see.
Our universe is a really violent place, and something exceptional happened on December the 27th.
That's right. There was a giant flare from a weird object called a magnetar, tens of thousands of light years away towards Sagittarius. It's an extreme version of a neutron star, the remnant of a massive star which has died and exploded in a supernova. And only a handful of these magnetars are known, and only a handful of them give out flares of gamma rays, as this one does. And this was the most extreme event ever seen. It was seen right across the spectrum from gamma rays through to radio.
And had that been close to us, a few light years away, that would have destroyed all life on Earth.
Luckily, there aren't any possible sources near us.
Just as well.
Yes, absolutely.
Well, that wasn't seen, obviously, but it was detected. And there are other observers now being put up, and one right at the South Pole, the Ice Cube telescope.
That's right. This is a weird telescope to look at neutrinos, very light, very fast-moving particles emitted by the sun, among other things. An ice cube, when finished, will be using a whole cubic kilometre of ice, a huge amount of material, to detect the passage of these neutrinos through the Earth. And the first detectors have just been put into place.
Chris, thank you very much. And now on to our main theme. First of all, though, a brief overview of the solar system, divided into two well-marked parts, Sun in the middle, 4 small planets, Mercury, Venus, Earth, Mars, then a bit of small bodies called asteroids, then the 4 giants, Jupiter, Saturn, Uranus, Neptune, and one maverick, Pluto. Now, we found recently that in the region of Pluto, there are many of these small icy bodies, which we call the Kuiper Belt. And much, much further out, so we can't see it, we think there's another belt there, or a cloud called the Oort cloud. And welcome to our 2 guests, Dr. Allan Fitzsimmons and Professor Iwan Williams. Now, remember that lovely Hale-Bopp comet some years ago? A lovely comet hung in the sky for months. And That came from a long way out.
Hale-Bopp was a new comet which came from what we call the Oort cloud. The Oort cloud we've never seen, but the fact that comets like Hale-Bopp come from somewhere tell us that we must have a big reservoir of comets out in the far reaches of the solar system, very far away. And from time to time these new comets come in from this cloud and we see them as this brilliant spectacle like Hale-Bopp.
How far away is it?
It's at about 40,000 astronomical units away from us. That is 40,000 times the distance of the Earth from the Sun. We probably think it formed through material on the outer edge of the solar system, being pushed out a little bit to larger distances, where speeds are now very low, and therefore you need only very little changes to change the orbit very much. So we think the Oort cloud formed by this material just getting excited by all sorts of perturbations, passing stars, galactic tides, possibly even things in the solar system itself, pumping up the eccentricity, making the orbits more elongated, making the inclination change so they go up. So the cloud, as we think of it today, is spherical, which explains why long-period comets come in from all directions. They can come in backwards and forwards and more or less perpendicular to the ecliptic.
They come in, what happens then? Do they go back?
Well, generally not, Patrick. What happens is that there are two forces or types of perturbation that act on Oort cloud comets when they come into the inner solar system. One are perturbations, gravitational perturbations by the giant planets such as Jupiter and Saturn. If they pass too close, their orbits will change. Also, when they come into the inner solar system, Oort cloud comets have ices on their surfaces vaporizing, and this produces a kickback, a rocket effect on their surfaces, which also acts to change the orbit. And they only need to have their orbit changed slightly to either be thrown completely out of the solar system or to actually end up on a much smaller orbit, and that actually is what happened to Hale-Bopp back in 1997.
I remember the very first Sky at Night programme in 1957. We had Comet Iwan Williams, and that been thrown out of the solar system altogether, so that will never come back. And then, of course, Shoemaker-Levy 9, that actually hit Jupiter.
Well, that's right. Shoemaker-Levy 9 was actually in orbit about Jupiter. Now, the problem with that is that it was only discovered after it went into orbit about Jupiter, in fact only a year before it collided with the planet. And so we have very little idea where it came from before then, whether it came from the Oort cloud or whether it came from somewhere else.
What about Halley's Comet?
Halley's is a funny intermediate comet.
Yes.
It goes around the wrong way, which suggests certainly that it is not a conventional short-period comet. On the other hand, it's not quite long enough for us to regard it as a long-period comet, like Hale-Bopp,
yes.
for example. So it's in some sense a mystery. It's sort of halfway house. We're not quite sure what to do with Halley.
The really big comets come from the Oort cloud, a long, long way away, but the short-period ones don't. They come from the Kuiper belt.
That's right. We knew by the 1980s that there had to be another source for comets, apart from the Oort cloud. One reason was because by that stage computers had got fast enough that we found our earlier calculations which implied that all comets came from the Oort cloud simply couldn't be true, and that the comets that reside within the inner solar system, the so-called short-period comets that take anywhere between 3 and 20 years to go once around the Sun, couldn't come from there. There was also the discovery of we were beginning to discover other bodies out there in the solar system, such as Chiron, the mysterious object that orbits
weird
between...
thing, isn't it? Yes.
That's right. It orbits between Uranus and Saturn.
It's quite big.
It's extremely large. It's perhaps 90, 100 kilometres across or so. And importantly, imaging of this object in the 90s showed a faint coma, a sign of a thin atmosphere around it, which implied it was cometary in nature.
There is now just a link between Kuiper belt objects, asteroids and comets.
We believe there's certainly a link between Kuiper belt objects and comets, because we believe that the majority of the comets in the inner solar system have come from the Kuiper belt. Over the history of the solar system, the perturbations generally from Neptune gradually erode away the Kuiper belt, and these objects either move outwards into interstellar space or they move inwards into the inner solar system to form comets. There may also be a link between comets and asteroids. That is less clear because we certainly see asteroidal type bodies that just appear as normal asteroids on orbits that we would normally associate with a comet. But it's still very much an open question as to how many of these bodies are comets, how many of these bodies are asteroids, and what is the real link between the two, something that we really do need to investigate in the coming decade.
One thing that interests me, in the asteroid belt and the Kuiper belt too, there are double pairs, binaries.
That's right. It's something we have discovered in recent years in the asteroid belt, but we're actually finding quite a few now in the Kuiper belt, as you say. Pluto, of course, is the most famous binary of them all, with its moon Charon. That's a third the size of Pluto itself. Now, in recent years, we've found other large binary systems out there, and for every one that we find, there exist quite a few more where we can't see that it's a binary because the secondary object orbiting the Kuiper belt object that we know about is just too small and faint. It's hidden in the glare. And we believe the reason that there's so many binary objects out there is because the Kuiper belt is such a collisional place where collisions are happening all the time, and these are probably the results of these collisions where objects have been split apart and broken up into two constituent pieces.
We've landed the spacecraft on one asteroid, Eros, but not so far on a comet. But we have now a probe called Deep Impact on its way to hit a comet, Temple.
That's right, Comet 9P Temple from the spacecraft. From Earth, we should hopefully, although we're not sure, see the comet suddenly brighten by several magnitudes and hopefully become very prominent in small telescopes and binoculars in the early evening sky.
We should point out this penetrator doesn't explode. It just goes in. I mean, some people think there's a bomb on board or something. There is not a bomb on board. It is just a missile which moves quite fast, which will hit the nucleus and penetrate.
And I wonder what it will show us. Is there any danger of disrupting the comet?
There's actually no danger of actually exploding it because the energy of the impactor is much less than the binding energy, the self-gravity of the comet. However, one possibility is that it's enough to fracture and shatter the comet in several different pieces. We won't know until we actually see what happens. Another thing that people have actually thought about and worried about is it possible it could be deflected onto a collision course with the Earth? Now, NASA has picked the comet very, very carefully, and it doesn't actually pass anywhere near the Earth at the moment, and the energy of the impact itself is also nowhere near enough to deflect it onto a collision course. So we'll be perfectly safe. We can just sit back and watch what happens.
A deep impact will hit Comet Tempel 1. What are the main things you want to find out from that?
Well, the main thing is that for all the comets we've studied so far, be it from Earth-based telescopes, be it by flybys, including Giotto, all we have seen is literally the surface. We've not seen what's inside the comet at all. We have no idea what the inside of a comet actually looks like. Deep impact will give us an opportunity of seeing down, certainly as far as the impactor will penetrate, will throw material out. We can see what is down there. The only other way of doing this will be from Rosetta at some time in the future, where hopefully the penetrating radar there will also tell us what's in the inside of the nucleus. But at present, we have no idea. It's like comparing studying a chimney sweep and seeing him with soot all over his face and concluding that it's made of carbon all through.
This weird thing, Sedna.
Yeah, Sedna has opened a whole new chapter in searching for objects beyond Neptune, because most of the objects we see in the Kuiper belt do come in fairly close to the planet Neptune. However, Sedna's closest point to the Sun is about 76 astronomical units away, so it never comes anywhere near Neptune. And one theory of its origin at the moment is that it was something that was put in that orbit from the passing of a close-by star shortly after the birth of the solar system, when perhaps the Sun was part of a cluster of stars. But of course we have no real evidence for that.
Well, Sedna takes over 10,000 years to get around, doesn't it?
That's right, and that's one reason why the orbit is still a little bit uncertain, because we've only followed it around a minuscule part of its orbit.
Well, what about Pluto? Discovered in 1930 by my old friend Clyde Tombaugh, and some time ago on a Skype night, I talked to Clyde about it.
I was not sure that it was in that neighborhood, and when I embarked upon it, I thought I would go all the way around the sky, searching it very systematically, and see whatever would come out. and whether it was a predicted planet or even some others. And so that was the basis for making the search.
And Pluto now, smaller than our moon, is it really a planet or isn't it?
Well, first of all, when he discovered it, everybody thought that Pluto was quite big,
Oh, yes.
bigger than the Earth, and therefore at that time it certainly was a proper planet.
Yes.
There was no question about it. It was much later when a satellite of Pluto, Charon, was discovered that we were able to get a good measurement of the mass of Pluto. And as you say, it now turns out to be much smaller than our moon. Also, its orbit is no longer unique in the sense that there are lots of Kuiper belt objects moving on an orbit very similar to Pluto, the same distance from the Sun, in the same resonance, that is going round twice for every 3 times of Neptune, and there are by now over 50 Kuiper belt objects on some such similar orbit. And therefore it is interesting to ask whether Pluto is still a planet or a Kuiper belt object, or maybe both.
What exactly is resonance in this sense?
The resonance we're talking about is where the time the body takes to go around the Sun is an exact multiple of the time Neptune goes around the Sun. And the importance of this is that it prevents the body ever getting close to Neptune, because they're going in this nice synchronous dance that they never get close.
The interesting thing that a lot of people don't realise, because of this resonance, as Ewan's described, between Neptune and Pluto, is that Pluto actually gets closer to the planet Uranus than it ever does to the planet Neptune, because it always stays so far away from that planet, even though their orbits overlap.
Pluto may or may not be a proper planet, but it does have an atmosphere of sorts.
Yes, certainly when it was close to the Sun, there was a very clear atmosphere there, which one could see. As it moves further out, it now becomes an interesting question whether the atmosphere will persist, whether it was caused by ices being melted by the heat of the Sun at perihelion, whether this will continue as it moves towards aphelion.
Bear in mind that Pluto takes 248 years to go around the Sun.
Yes, so we may well see the atmosphere for a fair number of years yet.
Pluto's a long way out, but we are planning to send a spacecraft there.
That's right. This time next year, NASA hopes to launch the New Horizons mission to Pluto. And depending on the exact launch date, it will take 8 or 9 years to get there via a swing-by of the giant planet Jupiter. Now, even if it doesn't make that launch window in 2006, it can still be fired off directly at Pluto the following year. But then that would take actually a few years longer and wouldn't reach there until 2019. So we may have a bit of a wait, but we really do hope that within the next 20 years we'll have the first close-up images of Pluto.
Alan, Iwan, thank you very much. Next month we have something very special for the first time. We're going to have a star party down here. And if you've been taking the photographs, do let us have them. And here's the address, skynat@bbc.co.uk. So next month, our star party, and let's hope for clear skies down here at Chelsea. Until then, good night.